So we're given this system, and we want to firstly find the difference equation giving this system. So Charles, does the difference equation depend upon what our particular input is? Do we need to know that our input is, say, this in order to find the difference equation?
No, sir.
Correct. Our difference equation just describes the system, so it should be completely independent of what a particular input or what its particular output is. So let's start off with a method to figure out how to do that. And the method that I'm going to say to go from a block diagram into a difference equation is, again, notice that difference equation is a whole lot like a differential equation, and it is the discrete time analog of the continuous time differential equation. So the first is give your signal line a name, like W of n, just before every delay element. And then name it correspondingly after the delay. So if it was W of n before the delay, then after the delay, it would be, Gordon, W of
n minus 1, sir.
Yeah. Now, once you've done that, you're going to write an equation around each summer. Say at the output, and you'll sum the inputs. It's almost like, this looks a lot like doing a KCL. It's almost like doing a nodal. And then put in standard form. And in standard form, what I'm talking about is putting y of n on the left and x of n's on the right. So let's do it for this. We have a, looks like this is already labeled, right? We already know this is y of n. So this is one common mistake I see cadets do. They'll not use existing nomenclature, and then by adding new variables, things get just impossibly hard really fast. But if that's y of n, then this has to be y of n minus 1. So we don't really even need to then create a new symbol for before this one, because it's already labeled. So this is just going to be y of n minus 2. So that was step one. If it was a more complicated system, or if, say, y of n was tapped off to the right, then we'd have to, no, even then we could do it. If it was a more complicated system where y of n was tapped off with more delays, sometimes you might need to write a w of n before a delay element if it wasn't named. It can happen with a more complicated system. And now let's do the second step. So the second step is to write the equation around every single summer. So let's start off writing it around, there's only one summer right here. So what that says.
So what do you mean by summer?
A summer is this, something that sums.
Oh, okay.
So we've only got one summer here, so we're only going to have one equation. Now, if we had a more complicated system that had 16 summers, you'd have 16 different equations. But here it's pretty easy. It's going to be the output, and the output is labeled, has got to be the sum of the inputs. And the sum of the inputs are x of n and fois. Give me another one.
X of n minus 1.
Who do you have in your background? Is that you?
Sir, that is Rad Rudd. He does not exist anymore.
I see. He's just the ghost looking over your shoulder. All right, so yeah, you've got y of n minus 2, and then you've also got this minus a quarter of y of n minus 1. Any questions about that step? You're going to put our standard form on the left with y of n's on the left, so it's y of n minus, let's say, plus 1/4 y of n minus 1 minus y of n minus 2 equals x of n, and you're done. Questions about that? If you look really hard at it, you can almost see the ghost of a differential equation in there. It looks an awful lot like what you studied in differential equations, where you'd have y of t plus a quarter y derivative of t minus y double derivative of t, things like that. Okay.
Terrifying.
It is. But isn't this kinder and simpler than differential equations?
Definitely.
All right, so we found the difference equation. Let's now find y of n for 0 is less than n is less than or equal to 2. This is the kind of thing that next exam block, once we cover frequency domain methods, you will look at this and in less than 60 seconds time be able to derive an equation for what y of n is in general for any value of n. But we're not there yet. So we're going to have to do it the old-fashioned way, which is painful and by hand.
Sir, I have a quick question.
Shoot.
About the way you reformatted that.
Yes.
Is there something that makes it easier the way you reformatted it? Like, would you use that specifically, or would you rather keep the y of n by itself on the left side?
Yeah. I want the y of n's on one side, and I want the x of n's on the other, just for now. But I hear what you're saying. You are saying, if we change this, or what Alex is saying is, wouldn't it be nice? Okay, big picture. We could write the difference equation as this, or we could solve it for y of n, right? We could say it's equal to, we could keep it exactly the way we had it up here. I'm not going to rewrite it again. The benefit of doing it at the top is that then you can start to grind through and solve for outputs of y of n given an input of n. The benefit of doing it down below, putting it in standard form, isn't apparent now. It'll become apparent when we talk about frequency domain methods. And just like you used a Laplace transform in signals and systems to transform circuits, you'll use Z transforms to transform these. And when you use Z transforms, you want to have Y's on one side, X's on the other. But let's now use what Alex suggested to solve for our output values. So the question says that for the particular value of x of n equals n squared u of n, in other words, x of n, the first few values will look like, it starts off with lots and lots and lots of zeros, right? Because it's multiplied by u of n. But then for our very first value, for our index 0 value, it's still going to be a 0. We plug in 0 for n squared, we get 0. But after that, we're going to get a 1, and then we'll get a 4, and then we'll get a 9, and it'll go on like that. And it asks to plot the output values for n equals 0 to 2 inclusive. So here's 0, 1, 2. So we don't even need to get this 9 part. That's as long as we get the output for those first few, we're set. Because we only have delays in our block diagram, does it have to be causal? All that we're doing is delaying inputs. That's definitely going to be a causal system. Because it is causal, and that's an easy way to check on a block diagram. If you see z to the positive numbers, it's not causal. If you only see z to the negatives, or you don't see any delays, it has to be causal. Then our y of n, we know is going to has to be zeros before we get our input. But what's y of 0? So using Alex's method over here with this first equation, we can say it's equal to x of 0 plus y of negative 2 minus 1/4 y of -1. And our x of 0 we know is 0. Our y of -2, you can see it's all zeros out there, minus 1/4 times 0. And so that's going to be 0. And so our y of 0 is going to be 0 too. That's not going to be true for our y of 1. That's going to be x of 1 plus y of -1 minus 1/4 y of 0. So x of 1, however, is 1. Y of -1 is still 0, and y of 0 is still 0. So now we get 1. And you can continue this on for the next one too. Y of 2, which again from our top equation is going to be x of 2 plus y of 0 minus 1/4 y of 1. So x of 2 is 4, y of 0 is 0, and y of 1 we said was 1. So that'll be 3 3/4. So that is our answer to the question. Questions about that?
Question 2B, it said to plot the results. Just for time's sake, you didn't plot them, but you would want that on a stem plot for the
That's right.
discrete. Okay.
That's right.
All right, those are
let's-
my only questions.
And just for completeness sake, let's just do it quickly. So y of 0 would be 0, and then it would be 1, and then at 2, it would be 3.75, and this would be n, and this is our y of n. And you know it's going to be 0 out here.